In this video I want to update you about what I've been doing with my first coil gun attempts. In the last video I used a 16 gauge coil, which is this one here. Very short, very few windings, and was getting huge amounts of current and a lot of sparks, and with melting of the switch and the wires when this thing was connected to a 1500 microfarad bank of capacitors. So a lot of wasted energy, but it was still able to send a projectile, this one here, fairly well, and into some styrofoam. I tried this one, which is 26 gauge wire, much more turns, like 200 turns, and most of the energy was lost as heat. And it sent a much smaller projectile with some good energy, but a lot of wasted energy as heat. So what I've done now is I've modified the whole setup, and I've made some different coils. So I'll go through these coils. This one measures out at 20 microhenries. It's 5 centimeters in long, and it's 16/8 WG wire, and it's wound around a, this is actually a ballpoint pen that I've cut the ends off. And that has just the right diameter and internal diameter as well to fit this projectile that I used with this straw. Then what I have, I've made some other coils. This one is shorter. This is 4 centimeters, much more windings, and I've covered everything in epoxy. So it measures out at 150 microhenries, whereas this one was only 20 microhenries. So you've got a lot more inductance on this one. It's shorter, and we'll test this one out. And then I made a larger one. This one's 350 microhenries. It's the same diameter, but it's 5 centimeters long. It may have actually one more extra turn of wire on it, so it's worked out at 350 microhenries, again 16 gauge wire, and 5 centimeters in length, wound around a ballpoint pen. This is just wood that I cut and drilled for containing the wire, and this one's covered in epoxy too. This one's actually still drying. So let me just show you how this thing is connected. So I'm using a connector strip here, and then basically when you have a surge of power from these capacitors, there's a lot of current going in this coil, which sends the projectile forward, and then projectile moves forward. You've got a residual magnetic field, which then collapses and then sends a reverse current back through the wire and reverse charges your capacitors. So to avoid reverse charging the electrolytic capacitors, which would shorten their life, what I've done is put this is a very fast diode. It's a UF 860. It's like a freewheel diode, and it can handle quite a bit of current and a high voltage. And I've actually put this across the coil and in series with a 1 ohm resistor. When I tried to do this without the resistor, the current blew up. That's what ended up happening to the diode. So it blew up a few of these diodes because I couldn't figure out why it was doing that. And I actually connected 2 of these together in parallel, and it blew both of them up. So, but with the resistor, it seems to not do that, and it still protects the electrolytic capacitors. And then I realized that if I was going to use this with a variac, this would be fine. But if you want to plug it directly into the outlet, you're going to get these capacitors essentially act as a short circuit, especially when they're completely discharged. So it's like short circuiting out the diodes. These are power diodes, but there's a risk of them failing with very high currents passing through them beyond what they're rated for. So what I did was I connected a resistor. This is actually a 10 watt, 10 ohm resistor in series with the outlet. Here's the outlet coming in here, in series with the outlet, and in series with this. So it reduces the amount of current and prevents that current surge. And this thing does get hot when you plug it in, but we're only plugging it in and then switching it off, and then you're firing it. You're not going to be firing it with this thing still powered. Otherwise you're going to blow up your diodes and short out the coil. So let's see how this thing works. What I did, another modification too, I put a little magnet there so that when I put my ion projectile in here, it sets it at just the right distance back. You don't want it right in the middle. You don't want it too far in or too far out. You want it just a little bit out, just so that the tip is getting into this coil. And I found that distance experimentally by moving the projectile back and then moving it more in and then firing this thing and seeing which one gave me the most amount of penetration of the styrofoam. So let's try this thing out. I'm going to load it up. We're going to put the thing in. You can just drop it right in the front, tip it back, tipping it back, gets it right in, and you can just adjust it a little bit to more optimal distance. When I first did this, I was using this particular coil, and I was using an SCR right here. That's my SCR. This thing is now dead. This one is rated for 200 amps. It's a C220D NJS, rated for 200 amps and probably at least 1,000 amps pulse. But because this inductance is still relatively low, the current surge going through it destroyed it. So it's now toast. And I've got some more on order. I've got some higher rated ones that are rated at 1.5 kiloamps, and those are still on order. So for now I'm going to use this, just a nail touching this piece of wire to make a contact, and we'll see. I want to see how it penetrates this piece of styrofoam. It's about reasonably thick styrofoam. I'm going to aim it and fire. So let me just show you how I charge this up. So to charge it up, what I do is I just basically do that and that. That's it. That's all it needs. And when I touch this 10 watt resistor, it's already started to get hot just from that one press. So now what we're going to do, we're going to fire that projectile into the styrofoam. So let's go. Here goes. So that looks like it went right through, or almost through. Good bit of energy there. And we're going to repeat that with these other coils. I'm going to actually just use the first coil, the 4 centimeter, 150 microhenry coil. So we're going to swap these out, and I'll get back to you in just a sec. Okay, I've just added the larger coil in, and I've secured it with some zip ties right there. And what I've done is I've also shortened the wires. One of the things about this is to keep all the wires as short as possible to avoid loss of energy in the wires. Okay, what I did here is I added another magnet because now we've got a larger coil, so the projectile is further away from it's actually further away from the magnet, so you have to raise the level. And also the dimensions have changed a little bit, so I've got the projectile a bit more forward. And what we'll do now is test out this setup with the damping resistor on the charging of those capacitors, and with everything else in place, and with this larger coil that's 150 microhenries. We'll see how it does with this much thicker piece of styrofoam, and we'll test that out now. And again, we're using 1500 microfarads of capacitance, so not a whole lot of capacitance. So let's charge this up. Okay, that's charged. And let's fire this thing off and see what it does. So it went right through, and there it is. And it actually hit that, which is not a good thing to have behind this, but it hit that tank of propane. So that's a little risky. I'm going to have to change that, but it's gone right through and bounced off the propane tank. So quite a bit of force in that, enough to drive it through a couple of inches there of styrofoam and to hit the propane tank. Luckily that thing didn't penetrate it. So anyway, it's definitely performing better. And once I get the new bunch of SCR switches, SCR diodes. You know, this thing unfortunately is dead. Otherwise I'd love to have tried this, but we'll see how that goes. Future plans are to use 10 of these bigger capacitors connected in parallel for a total of 4,700 microfarads, up from the 1,500 microfarads that I'm using here, and also to use a larger coil with 16 gauge wire, and then to use an SCR for the instead of that mechanical switch, and with the bigger microfarads, with the bigger microhenries on this coil, that should reduce the amount of current, so I won't run the risk of blowing my SCR diode. So that's the plan, and I'll have a video once I've got that up and running. But for now, at least this tests well, and once it has a soft switching device, an SCR, this should work even better. One of the key things about these units is that you want to make sure that that projectile is positioned just right, because you want to drain all that capacitance and have a collapsing magnetic field by the time that's in the middle of the bore of that coil. If the magnetic field, if you use two bigger capacitors, like if I went to 10,000 or 20,000 microfarads instead of 4,000, I run the risk of the projectile going past the middle of the bore of the coil and having the thing suck back in. So I'm actually going to lose power. So you have to get the magnetic field, the number of turns of coil, the length of the coil, the length of the projectile, the amount of capacitance, all correct and optimized in order to get this thing to work efficiently. And even when it's working most efficiently, we're not talking about a very high percentage of efficiency. So anyway, thought I'd just show you that, and check back with me for my updated one with this new batch of capacitors that just came in from eBay, and my new coil here with a bigger diameter, more turns, and with soft switching. Thanks for watching.